To begin with, as you can see here on the right side, we have two circles. One that is painted just a solid gray color, using a combination of titanium white and any black paint. And the other circle on the right side is a combination of three separate colors, one of them being bright red, one of them being ultramarine blue plus a tiny bit of titanium white, and the other one being a mixture between bright yellow and a tiny bit of primary blue. Now, as you noticed, one side, the gray is just a solid color throughout, whereas on the right side, there is no gray at all. It's all just those three colors exclusively using pointillism. And what you'll find unique about these two circles is that when you look at them up close, they look distinctly different from one another. But as you can see here, when I move the camera back further and further, the two colors start to look the exact same. They both look gray from afar. So there's a few questions that do come out of this. The first one being, why does the circle on the right look gray from afar? And the second question is, if we consider gray to not be a color, then should the circle on the right also not be considered a color, even though it's only consisting of colors that we do define as colors, red, green, and blue? It's quite intuitive to understand that we do need some kind of light source to be able to see the colors of anything around us. And there's a very important reason for that. It all has to do with the nature of what light actually is, and how light functions in our world to give us color. You can imagine EM radiation as a series of many tiny balls that fly away in a straight line from their source object. These tiny ball things are usually referred to as photons, and they all happen to travel at the exact same constant speed, which is about 300,000 kilometers per second. Now, it would be a bit of a mistake to just call photons, these particle-like balls moving through space, as another very important property of them, one that happens to be a lot more significant for visual artists such as myself, is that they each have a unique wavelength depending on how much energy the photon itself holds. It just so happens to be that when a photon has a wavelength of about 400 nanometers, it appears as the color purple when it hits our retinas. And as that wavelength continues to increase, the color shifts along the Roy-G-Biv scale until it reaches a deep red at a wavelength of about 700 nanometers. When we take a look at a more prominent light source, such as our own sun, we can see that it always shines a very brilliant white within our sky. Now, side note, never look directly at the sun because it can damage your eyes. But the reason it shines so brightly white is because it doesn't necessarily just emit photons of one particular wavelength only. It actually emits photons of a wide range of wavelengths. And here in this chart, you can see which wavelengths are a lot more prominent than others. The wavelength group that is the most prominent happens to align with the visible spectrum. Now, it really isn't a total coincidence that many of the sun's photons have wavelengths within the visible spectrum. It's actually because of these photon wavelengths that our eyes have evolved over time to be able to detect these photons and transmit them into our brains in the forms of shade and color. Within our eyes, there are these things known as cones, and what they are is that they're tiny little cells that are able to easily detect photons with wavelengths within the visible spectrum, so long as there's enough light in the area, which is why you can't see color when it's dark outside. The L cones are a lot more sensitive towards longer wavelength photons, which allows us to see what we perceive as red. The M cone cells absorb medium-sized wavelengths, which we perceive as the color green, and the S-cone cells absorb shorter wavelengths, which form the color blue in our minds. Now notice that we don't have any cone cells for the colors in the rest of the Roy-G-Biv set. So what happens is that when a photon corresponding to, say, the color yellow shows up, our cones corresponding to both red and green are both strongly sensing that light. So the brain is aware of this, and that sensation that comes from the L and M cones creates a mental picture of what yellow would look like. And in essence, all of the colors we can picture in our minds are just a result of a combination between the sensational strengths of each of the three color cones. So what happens when we mix up a solid gray color is that we are mixing up a substance that is able to absorb specific sections of the Roy-G-Biv set. This gray paint ends up reflecting a smaller amount of the photons back, with specific wavelengths ranging around the areas where the three cones are the most prone to sensing light. This is similar to the reason why our sun looks white to us, since the mixture between all the Roy-G-Biv color waves combined will let our eye cones signal to our brains to form that brilliant white in our minds. That is why scientists will often refer to the color white as being the sum of all colors together. The idea of mixing photons at different wavelengths in order to form more colors is what we know as additive mixing. Additive mixing is most commonly used within TV screens, where the engineers basically combine various levels of red, green, and blue light from each of the subpixels on the monitor to form any specific color that they choose. This process is very similar to my red, green, and blue circle at the beginning of the video, where as we kept moving back further from the circle, the color dots eventually became too tiny for our eyes and my camera sensors to distinguish between. That's kind of why we saw gray instead of just red, green, and blue at the end. And the reason why we saw gray instead of white is because with paints, a lot of the light from the sun ends up getting absorbed, which forms a darker shade. And you can contrast that with TV screens, where they emit their own light, which causes the shade of white to be much brighter and closer to the true value of white. So what we've learned today is that gray is not necessarily a color in terms of having one specific wavelength of light. Rather, it is a combination between multiple photons with various wavelengths associated with them. So the best way to describe gray and other mixtures is just being a mixture of light waves with different color values associated with them. I hope you learned a lot today, and as always, thank you for watching, and have a good one.